In this video, we're going to concentrate on low-level wind shear events associated with microburst activity. Some of my early days of research was dealing with this phenomenon. I was the radar field manager for the UND Doppler weather radar for about 10 years. I did field research and was in on the ground floor of developing algorithms to help use Doppler radars to see these low-level wind shear events, especially around airports. So the first one we'll get into is the dry microburst. And for that occurrence, you need a system where we have precipitation falling into drier air below. And the precipitation will mainly evaporate before reaching the ground, and that's what we call virga. And then this cold air could continue to descend and hit the surface and then diverge upon impact with the surface. So here's an example of a dry microburst in the north of Denver, Colorado. The front range of the Rocky Mountains is a favorable spot for dry microburst activity due to the fact that the thunderstorms can be a little bit higher in elevation, or I should say the base of the thunderstorms. And the front range of the Rocky Mountains is noted to be a semi-arid type climate, so the dew point temperatures could be rather low, even though within the thunderstorm complex you'd have 100% relative humidity. So the chance of creating virga was pretty good, and then that descending cold air could cause your low-level wind shear event. So one of the signs that you have to look for the dry microburst is the presence of virga. And then if, in this case, if you can see dirt moving and diverging away from the cloud formation, that's a hint that indeed low-level wind shear is occurring on the surface. So there's Mike. He was in the right spot at the right time. He took these still photos of a microburst event occurring, and let's just run through these. What was unique about this situation was you can see that there was a bright spot or an opening within the clouds indicating descending air, and the occurrence occurred over a field that was not planted, so we call this summer fallow. And so Mike was able to see the air moving the dirt around in the field and give some visibility to the microburst. Now the category of a microburst, it's a rather small feature. We use 4 kilometers for the horizontal diameter, so that's about 2.1 miles. And then if it gets bigger than that as it spreads out, then we flipped the category from a microburst to a macroburst. Okay, so let's run through these photos. Here you can see the air starting to reach the surface, and I drew in some arrows to help visualize which way the dirt was moving. So we have a divergent pattern, and hence we have our microbursts. Now microbursts can come in different categories. We typically want to start with differential speeds of around 20 knots for the weak microburst, but I'll show you some of the more severe microbursts that I've captured on our Doppler weather radar. So as we move through the sequence, here we can see where we had an impulse of a stronger downdraft, and that was able to push the dirt even harder, and it flipped it even higher into the air. So these microbursts can also impulse over the same area. So you can see that there's kind of an eddy on the leading edge. The air is kind of coming up and curling back over the top as it diverges away from the downdraft point. And then as it spreads out a little bit further, we could flip it to a macroburst. So the this area continues to spread out. and then boom, we get another downdraft in this vicinity, and you can see the beginnings of another microburst as the first microburst spreads out and goes into a macroburst form, and eventually the dry microburst will dissipate. So these are not long-lived situations. Typically, if I'd had to guess, I'd say a microburst might last around 5 to 10 minutes before spreading out and weakening. But again, you could get impulses which could continue the event to be a little bit longer than that 5 to 10 minutes. Okay, now the wet microburst is when the precipitation core and the associated downdraft will make it to the surface, causing the divergent outflow pattern. Not all descending rain shafts, though, will cause this divergent outflow pattern. So we probably need some precipitational cooling within the rain core. And we also have this phenomenon called precipitation loading, some frictional factors which could aid in the downward motion. And then when it hits, it has to diverge in all patterns. So here's a precipitation core descending, this ball feature. And when that hits, it will spread out in all directions. And so the arrows that I drew in show the movement, and then this is the eddy on the leading edge of that wet microburst. And you'd also have the same thing over here. I just didn't, it's not centered, but you'd have an eddy come and kick over on this side as well. So the problem we have when these microbursts are in the vicinity of an airfield, aircraft are pretty vulnerable on takeoff and landing. And so if one of these microbursts would be sitting out on the runway or out on the edges of the runways, let's say within 2 or 3 miles of the runway complex, and an aircraft had to go through one of these features, it would encounter a lot of low-level wind shear. So in this particular situation, the aircraft, in this case we have it 0 to 4 kilometer is this particular distance. The airplane would encounter a pretty strong headwind as it enters the microburst. Now the situation about the aircraft, this one is landing, they're in a vulnerable position. The wheels are most likely have been dropped for landing, which adds friction to the aircraft. The aircraft is basically flying as slow as it can, but still maintaining lift as it slowly descends on the glide slope onto the runway. So if it does encounter, like in this case, let's make up a number, let's say like a 20-knot headwind, well, that's going to cause added lift over the wings, and that's going to bring the nose of the aircraft up, and it's going to want to lift. Well, the pilot, to get back down on that glide slope, would most likely have to cut power and to bring the airspeed down, indicated airspeed down, and bring the nose back down. So as they do that, just within 1 kilometer to 2 kilometer distance, they'll be in the downdraft part of the microburst. Now that's going to cause a pushing sensation, and if they did cut power back here, it's going to be difficult to regain power once they get into the downdraft. And then a little bit further along, about another kilometer into it, they'll encounter the downdraft. Now they got a tailwind component, and so they're losing more lift, and they're still trying to regain the power that they cut back here. And if they're not successful, they'll stall, and that aircraft will hit the surface of the earth before it actually gets to the runway, which might be located right over here. So that's the makeup of the aerodynamics in play with these aircraft battling this low-level wind shear event. So we did some research, the history of it. I was in Memphis, Tennessee, already doing some research with our Doppler weather radar back in 1984 and 1985, long time ago. I was a young lad, but I was in Memphis, Tennessee, and in the fall of 1985 we had a bad aircraft accident in Fort Worth, Dallas, where an L-1011 crashed due to this wet microburst phenomenon. Um, and the FAA was very concerned about these planes going down in these wind shear events. They were happening not more so than the United States. Obviously, they're happening around the world, and they posed the question, to the research faculty around the country: can we solve this problem? And a lot of us were already using Doppler weather radars, and we knew we could see these features on the Doppler. And so we proposed to the FAA that I think we could develop Doppler weather radars to automatically find these features and give pilots warnings. So this was back in the mid-1980s. So we move ahead. In this case, now we're up to 3 years later, 1988. We switched the locations, and we're now located in Denver, Colorado. And at that time, Denver International Airport wasn't built yet, which is currently out in this vicinity. But we had old Stapleton Airport in the metro area of Denver. We started to do wind shear alerts for pilots in the summer of 1988. Now, it wasn't automated yet. We had to use telephones and aircraft radios to give these pilots warnings. So just to give you the setup, the UND radar site was located in this facility, in this vicinity, looking into Stapleton Airport from the northeast. And then we worked with MIT and Lincoln Labs, and their radar was located in this vicinity on the Buckley Air National Guard base, and they were looking into the Stapleton Airport from the southeast. And with that, we can combine our two radar beams, and in post-analysis we could look at the three-dimensional wind field in a process called the dual polarization. Now the situation was these microbursts, as they diverge, and let me blow this up a little bit for you. The microburst downdraft to be in this vicinity right here, and the air is going to move in all directions. But as your radar beam sweeps through this area, let's say the dish is rotating in that direction, we can only pick up the component that is parallel to the radar beam and away from the radar beam. If it's perpendicular to the beam, then you actually see zero velocity. So you get these butterfly type patterns, and if the zero line is perpendicular to the radar radial here, then you know you have divergence. And so that was the makeup for the microburst. Now MIT down here, they'll see the toward component in this direction and the way component over here, and so their zero line is going to run in that direction. So some of these microbursts aren't symmetrical, they're asymmetrical. So sometimes we will see the major axis. Sometimes MIT Lincoln Labs would see the major axis, and we'd see the minor axis. So on this situation, let me back up. We had a pilot coming in from the east. Air traffic control gave that individual clearance to land, and we were monitoring a rain shaft about 2 miles off the end of the runway, 2 to 2.5 miles off the end of the runway. MIT Lincoln Labs, they were the main players, and Mark Eisminger was operating that facility as I was operating the UND facility. So Mark was making the calls to the tower to put out the warnings to the pilots on final approach. And on this particular microburst, Mark Eisminger relayed to air traffic control that the pilots would encounter 30 knot loss on 2 mile final. Well, I was watching the situation, and I noticed that our radar, looking at the maximum toward and the maximum away, I was seeing 50 knots at the 2 mile mark. So I had to quickly call Mark Eisminger. Mark, upgrade to 50 knots. Mark calls the tower, upgrade to 50 knots. Tower relays the information to the pilot. 50 knot loss on 2 mile final. So that's how we work the operation. Now, for the future pilots amongst you, when air traffic controls give you clearance to land and there's no obstruction on the runways. Obviously, it's your runway. So you, the pilots, when you get a wind shear warning, you have to make the decision how you're going to handle it. Are we going to progress and land, or are we going to ask for a go around and divert landing and maybe come back in and try a second time? Now, this particular pilot decided to fly through this event, and when he hit the headwind in this area, the plane did lift like it would due to a stronger headwind, and then when he hit the downdraft, the plane started to sink. Now, the good news is the pilot did not cut power as they migrated into the center of the microburst. So they still had power to maintain lift even when they got into the tailwind component of the microburst. Now, the pilot was able to get to the runway and was able to land, but the ground speed was a lot quicker than normal for a landing, and so the pilot basically did use up the whole runway to get that airplane to stop. And I can still remember listening to the aircraft radios, even though it was a lot of years ago. You could hear the nervousness in the pilot's voice of the experience that they just went through. So that was the beginnings. Now, today, all of this is automated. The Doppler radar will pick up the signal. It'll notify air traffic control that there is a wind shear event in the vicinity of the airfield, and then ATC can report that information to the incoming flights. And the pilots are much more educated in microburst and low-level wind shear events as well. So here's Jason just sent in this photograph. As you know, we do have some satellite facilities around the country, the University of North Dakota Aviation Program. And this 90-knot microburst hit the tarmac with the planes just idle on the tarmac, and it did damage quite a few of the aircraft as it tipped them over. And Jason even said some of these aircraft were tied down, and they're still able to be damaged with that microburst wind. Okay, switching on to the wet microburst. This is a picture I took. Now we're switching locations. To help in wet microburst, we spent some time in Kansas City, Missouri, and we also spent some time in Orlando, Florida. This picture I took was just to the southeast of our radar facility in Kansas City, Missouri. So a nice thunderstorm complex, and the way the sun was shining, I was able to get the rain shaft. And then you can see right here on the bottom that the rain shaft was spreading apart, or that's our divergent signal. So I took the radar and I swung it around to this cloud, and I took the radar dish and I did one of these. I went straight up and dropped it straight back down. So that's what we call a range height indicator. So I did an RHI through that thunderstorm. So this thunderstorm, this is what it looked like on our Doppler weather radar. So again, I stopped the dish, went up, and then I came right back down. Did a range height indicator. So this is reflectivity on the bottom one. Top of the cloud, 54,000 foot above ground level. Pretty impressive. The white area, that's the highest reflectivities. Maybe making hail up in this part of the thunderstorm. And then this is the downdraft right here. So that's hail actually falling to the surface. Then you can see the reflectivity is kind of spread out in that direction. So that's your divergent flow pattern. That's with reflectivity. Now, how strong is the air moving at the base? Well, that's where this color coding comes into play. This will be toward the radar. That's the downdraft. And this area will be air moving away from the radar. So what I did next was I stopped the radar dish at low levels, and I just scanned right across that very low area. And that's a PPI, plane position indicator. And I just did a sector. I didn't have to do a full circle. And so I just did a sector to, here's the radar site, and to the southeast. And as the radar beam swung through here, this was the maximum toward velocity. The downdrafts right here, and this is the maximum away velocity. And again, we don't see much in this area because the wind movement was fairly perpendicular to the radar beam. So that spot right there, 62 miles per hour towards the radar, downdraft, and this spot 26 miles per hour away from the radar, and all that occurred over 1.25 miles. So if you take a look, adding those two together, 88 miles per hour, 76.5 knots over 1.25 miles. That is a very severe wet microburst. This occurred over a suburb of Kansas City, Missouri called Clay Como, and they did sustain some structural damage. And I still remember the newspaper the next morning said that a tornado struck Clay Como, Missouri. But indeed, Doppler radar didn't show rotation, it showed divergence, and so it was a strong microburst, not a tornado, that did the structural damage. And then this last one, up here in Grand Forks, can these things occur within our thunderstorm complexes during the summer season? And the answer is definitely. This situation occurred in the late evening hours, 10:07 p.m. Central Daylight Time, and the date, hard to read here, I'll read it for you, August 19th of 1994. So now we're back home. Our research days are pretty much over. The Doppler radars are being developed, both the NEXRAD systems and the terminal Doppler weather radar systems, and this is at the time when we decided to put the radar on top of Clifford Hall, where it still is located today. So the National Weather Service moved into Grand Forks in about 1996. So before the National Weather Service moved to Grand Forks from Fargo, Leon Osborne and I would help out with the monitoring severe weather during the summer season, and we'd help out with the ham radio operators and the spotter network in those days. And so being we had a significant thunderstorm activity in the vicinity of Grand Forks and Polk County, I was up in Clifford Hall, up in the penthouse, running the radar on this particular evening. And again, this would be Clifford Hall right here, where the radar site is. And so I put in the location of the airport as well. So this pretty strong thunderstorm with high reflectivities noted here in the white area, that did put down a microburst. And so the downdraft is right here. And this area toward the radar is 54 miles per hour, and this area in the blue right here is going away at 40 miles per hour. Now this microburst, let me clear it here, this microburst was in this location, and then it's moving in this direction as the thunderstorm cell moves in that direction. So at one time it was just sitting off the end, or roughly 3 miles off the end of the runway, the north-south runway at the Grand Forks International Airport. Northwest Airlines, and this is so long ago, Northwest hadn't been bought out by Delta yet, but Northwest Airlines was scheduled to land in Grand Forks at 10:20 that evening. So they're probably in the vicinity, lining up, probably coming, in this case, landing from south to north. If they would have been early, there's a chance they could have entered and moved right through this feature when it was situated a little back further over here. And if that aircraft would encounter that type of low-level wind shear, it'd probably be a high probability that they would not have made it to the airfield. There's a chance that airplane would have crashed probably just south of Highway 2. But luckily, they were either on time or a little bit late that evening. So by the time they got here to land that aircraft at Grand Forks, the microburst had moved in towards the city of Grand Forks, but it also weakened as it moved into the city limits of Grand Forks. So yes, microburst activity can occur here in Grand Forks as well. And in fact, this change in velocity of 94 miles per hour is one of the strongest microbursts that I've recorded on our Doppler weather radar system. Okay, so just to end the chapter, part 1 of chapter number 14, let's take a look at a couple questions. The aircraft shown in this image will encounter headwind at position A, downdraft at position B, tailwind at position C. Again, I'm doing this question just for those students that are not aviation students. So is this a headwind and a downdraft and a tailwind component? And the correct answer is all of the above. And this question, when observing these two items in combination, you should be aware of the possibility of a dry microburst. Not a wet microburst, we're talking about a dry microburst. So virga we need, but do you want high relative humidity values near the surface? Nope. We want low relative humidity values because we needed the evaporation process to kick in. Do you want a rain shaft and divergent flow at the base of the rain shaft? That would be the wet microburst. Rain shaft making it to the surface with divergent flow. That's the wet microburst. So the correct answer is C. We want virga. We want the lower relative humidities to aid in cooling the air below the cloud base. And then as that cold air descends, it'll cause blowing dirt and or dust because a lot of the precipitation doesn't make it to the surface, and so we'll see the blowing dirt. That is the dry microburst. So the correct answer is C. So I hope you enjoyed that video on the early days of detecting low-level wind shear. And again, we've come a long ways since those days back in the mid and late 1980s. So future pilots, you will be protected with the aid of Doppler weather radars and terminal Doppler weather radars around major airfields to give you a heads up on these low-level wind shear events in the vicinity of the airports. Okay, we're going to switch gears, and when we start video number 4, we'll talk about parameters that make a thunderstorm severe, and then we'll also go through different types of thunderstorm complexes.